अब स्टूडेंट्स बात चल रही है spread spectrum techniques की, and there are two basic techniques that we are going to be discussing. The first one is frequency hopping spread spectrum, and then we have got direct sequence spread spectrum, FHSS or DSSS. Students, discussion start करेंगे with the frequency hopping spread spectrum. Students, in this type of spread spectrum technique, you have m different carriers with m different carrier frequencies, and these different carrier frequencies are modulated by your source signals. Students, at one point, your source signal modulates one particular frequency, and at the next moment, it modulates another one. Students, slide pe chalenge and we will discuss this concept in detail. Once again, as you can see, the bandwidth that is occupied by a source after the spreading has taken place, which is shown by FHSS, is a lot greater than B. Students, the first step is the production of a k-bit pattern for every hopping period. So this pseudo-random code generator, students, this essentially creates a k-bit pattern. Students, this code generator, this is also called as pseudo-random noise or PN. It creates this pattern for every single hopping period, which is represented by TH. So every single hopping period, a k-bit pattern is generated. Students, the frequency table, it uses this pattern that is generated to find the frequency to be used for this hopping period. And this frequency table, we'll discuss this table in a little while, but this table then passes on this frequency to the frequency synthesizer. Students, the frequency synthesizer, it creates a carrier signal of exactly that frequency, and then the source signal uses a modulator and it modulates the carrier signal, and we get a spread signal which has got a bandwidth which is far greater than the bandwidth of the original source. Students, I told you about the frequency table, so let's talk about that a little further. Students, in this case, we have assumed that we are using 8 hopping frequencies, 8 different hopping frequencies. Students, for each one of those hopping frequencies, this is essentially a very low number of frequencies for real-time applications, and it's just for me to explain this concept to you, students. So M in this case is 8. The number of frequencies is 8, 200, 300, 400, 500, all the way to 900. And the k-bit pattern, in this case, the k is equal to 3. So the pseudo-random code generator or the pseudo-random noise, the PN, that we went through in the last slide, it will create 8 different 3-bit patterns for every single frequency that we have chosen for our application in this particular case. And then these are mapped to 8 different frequencies, as you can see in the frequency table. 200 kilohertz is mapped to 000, 300 kilohertz is mapped to 001, and so on. Students, note that in this particular case, the pattern is pseudo-random. What this means is that it is repeated after 8 hoppings. So at hopping period 1, the pattern is 101, for example. And then once you go through all the other patterns, the frequency selected against 101, which is 700 kilohertz, the source signal modulates this frequency. And the second one, second pattern selected is 111, and that is corresponding to your 9 kilohertz. The third one is 001, which is corresponding to 300 kilohertz. And after the 8 hoppings, the pattern repeats itself, and we start from 101 again. Students, in this particular case, you have got a concept of FHSS or frequency hopping spread spectrum cycles. Students, if you can concentrate, we have got some carrier frequencies on the y-axis, and then we have some hop periods on the x-axis. Students, if the number of these hopping frequencies that you see on the y-axis, if we represent this by capital M, we can multiplex M channels into 1 by using the same bandwidth BFHSS or frequency hopping bandwidth, and this is possible because a station uses just one frequency in each hopping period. So in one cycle you have got a hopping period 101, which corresponds to 900 kilohertz, and then after 8 cycles, as you can see, it repeats itself. And so we have got multiple cycles corresponding to multiple hop periods in frequency hopping spread spectrum. Students, another concept in this particular case is of bandwidth sharing. As you can see, we have got, in the case of FDM or frequency domain multiplexing that we have already studied, the frequency domain multiplexing has 4 distinct frequencies, and we can use these 4 frequencies to multiplex the FDM signal onto our line. But in the case of frequency hopping spread spectrum, as I told you, a station uses just one frequency in each hopping period, and for M different stations can use the same spread spectrum bandwidth if we can use an appropriate modulation technique in this particular case, which is FSK or MFSK, multi-level FSK, and so FHSS is pretty similar to FDM when we talk about this concept of bandwidth sharing. 4 channels on using the FDM, and we are still using 4 channels in FHSS. The only difference is that in FDM, each station uses 1/m of the bandwidth, as you can see, and in the case of, and that allocation is fixed, but in the case of frequency hopping spread spectrum, each station uses 1/m of the bandwidth, but in this case the allocation changes hop to hop. Every single hop has got a different allocation in FHSS as compared to FDM. Students, the second spread spectrum technique that we have got is the direct sequence spread spectrum. Students, direct sequence spread spectrum or DSSS, this also expands the bandwidth of the original source signal, but in this particular case, the method of doing that is different to frequency hopping spread spectrum. Students, in this case, we replace each data bit with n bits using a spreading code. Students, this spreading code is generated by a chip generator, and therefore this code of n bits is called chips, and the chip rate is n times the data bit. Students, as you can see in the slide, we have got a chip generator. The chip generator is generating a code of n bits, and this code is called chips. Students, as I told you, in DSSS, we replace each data bit that we have from the original signal with this code of n bits, which we also call as the spreading code. Students, once this spreading code or the chips is generated, we have got a modulator which allows the original signal to modulate this code of n bits. Every bit is replaced by this code of n bits, and we ultimately end up with a direct sequence spread spectrum signal.